Hi everybody, Mrs. Pesic here,
And Miss Bella here.
and we are looking at section 3.8, transforming polynomial functions. And your objective in this section is to do just that, transform polynomial functions. We have looked at transformations in chapter 1 and chapter 2, so a lot of the ideas in here, we're just extending the same transformation ideas to any polynomial function. So I don't think that it should come as a surprise to you that, for example, if you have some function and you add some number at the end of the function, that's going to shift either up or down depending on what that number was. But you also know that if you add or subtract a number to the x itself before you put it in the function, then that's going to shift your graph left or right. So for example, if you have x minus 2 quantity cubed, since it's an x minus 2 in the parentheses before it's cubed, that's going to be a shift 2 units to the right. Whereas if you have x plus 1 in parentheses before you cube, that's going to be shifting 1 unit to the left. We've done this with linear functions, and we've done this with quadratic functions. What about if we have a number that's being multiplied by the whole function? So the function's getting multiplied, for example, by some number a. Well, that is going to be your clue that this is going to be a vertical stretch or a vertical compression. If your a value was greater than 0, if your a value is greater than 1, it is a stretch. If your a value is between 0 and 1, like in this example, 1/2 x cubed, then it's a vertical compression by, in this case, by 1/2. Again, that's a vertical stretch or compression if you multiply the entire function by some constant. But what if you multiply just the x by some constant? Well, then that is your clue that you're going to have a horizontal stretch or compression. If the number in the parentheses with the x is between 0 and 1, like in this example, then you're multiplying 1/5 times x first, and then you're cubing, so that's going to be a horizontal stretch by 5, because remember, you need the reciprocals if you are doing a horizontal stretch or compression. Likewise, with this one, we've got a 3x in parentheses before we cube. That's going to be a horizontal compression of 1/3. And lastly, we have reflections. So if you have some function like f of x equaling x cubed, and you take the opposite of that function, the opposite of any function is going to be a reflection across the x-axis. But if you take negative x, wherever you see an x, and then you put it into the function, like negative x in parentheses cubed, then that's going to be a reflection across the y-axis. But you know, x cubed is not the best example to look at that with, because when you reflect the x cubed graph, which looks like this, over the x-axis, well, then it's going to end up looking like this, but guess what? That's the same as if I had reflected it over the y-axis. So not the best example. So let's take a look at a better example. What if we look at the function square root of x? So if I have my parent function square root of x, you know that looks like this. So here's my parent function square root of x. And if we have the whole function made opposite, so if we have, let's say, g of x equaling the opposite of f of x, then that's going to be the opposite of square root of x, and that's going to be a reflection over the x-axis. So that's going to look like this. So this is my g of x function. But if I had, for example, h of x equaling the f of negative x, in other words, I'm going to take all of my x's and make them opposite. In this case, that would be square root of negative x, and that's going to be a reflection over the y-axis. So that graph is going to look like this going this way. So this would be my h of x graph, and this one here is my g of x graph.
So now we're going to take a polynomial function, and in this case we'll have f of x equals x cubed minus 6, and we're going to write the rule for each of the functions after we perform some sort of transformation, and we'll sketch its graph. So to start off in this one, again, we're going to actually use this f of x, so this right here will be our parent function. So before we even do the transformation, why don't we graph that by hand? We know that f of x equaling x cubed minus 6 is close to, was related to the parent function for x cubed, which we know has the ordered pairs of -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. So that would just be on the x cubed, which means if I wanted to graph x cubed minus 6, I have shifted all of those down 6 units. So it looks like my ordered pairs, all of my y's will be less by 6. So I'm going to really plot the ordered pairs. Yeah, my x's will stay the same. I probably should label these x and y's here. So we know that our y's, so we're going to graph this one in blue here because that's going to act as my parent function for this one. We'll graph the points -2, -14, because again, I'm reducing each of the y's on my parent function by 6 units. -1, -7, 0, -6, 1, -5, and 8, 2. All right, so let's plot in blue what the parent function will be for this problem. So -2, -14, can't really fit it on my graph, but we do know that it would be somewhere, down here, somewhere down there. Okay, we're going to plot -1, -7, 0, whoops, that needs to be over a spot. There we go. 0, -6, 1, -5, and 2, 2. So starting off, this is our parent function, or this is our f of x in this case. Now, in order to perform our next transformation, I'm going to kind of move all of this stuff. We're going to group it up and move it out of our way for right now. We don't need to see that for what we're going to do. Whoops. There we go. So that was our work we did from before. So if we now want to figure out what is our new function g of x, how do we find that? Well, it says take f of x, and we're going to say plus 2. Since we have a plus 2 on the outside of the function, that is actually a vertical shift. And we know that vertical shift is up 2 units. So we're going to take each of our y values from f of x and add 2 to them. So now that we've kind of figured that out, we'll bring this back here for a second. And we'll say, okay, if I had all of my values right here on f of x, and I want to now shift it up 2, I'm going to add 2 to each of my y coordinates to figure out what my new ordered pairs would be. So on g of x, again, my x values are going to stay the same at -2, -1. Whoops. Let's undo. Oh no. Let's undo each of those two things. I need to control this from the computer over here. We're going to undo that line I drew in. Okay, and we'll just erase that out of here before we keep going. Okay, there we go. Now we're back. So our x's are going to stay at -2, -1, 0, 1, and 2. And we are going to say that our values for y are now going to be at, instead of -14, I'm now at -12. At -7, now I'll be at -5. 0 will now become -4. At 1, we'll be up at -3. And at 2, now we are up at 4. So these points here will be on my transformed g of x. So if I were to plot those, I'm going to plot them in green. I have the point -2, -12, again, which means it just comes up 2 units here. -1, -5, 0, -4, 1, -3, and 2, 4. So you should see it, we just took everything on our parent function, f of x, and we've just actually taken it 2 units and moved it up. And you could have actually done this from your graph as well, just move each point up 2 and plot those as well.
Okay, so let's do this next example. We're still using that parent function of x cubed minus 6, and this time we're going to transform it by doing f of x plus 3. So we know that we had this parent function in blue, which was -2 was down here somewhere at -14, and -1 was, let's get those ordered pairs back again from before, -7, and then 0 was -6. Here's 0, -1, -7, 0, -6, 1 went to -5, and 2 went to 2. Okay, so that graph, if I kind of draw that in, that graph looks something like this. But this time we want to do f of x plus 3. Since we're changing the f, we're changing the x by adding 3. This is going to be a horizontal change, and since the x is having 3 added to it, that's going to be a horizontal shift to the left 3 units. So this time, if we look at our parent function ordered pairs for the parent function, let's see, it was -2, -1, 0, 1, and 2, and it was -14, -7, -6, -5, and 2. But this time, if we want to shift to the left, we're changing all of the x's, and we're going to subtract 3 so we can go to the left. So I'm going to subtract 3 from all of these to get my new ordered pairs. So this is going to be -5 going to -14, -4 going to -7, -3 going to -6, -2 going to -5, and -1 going to 2. So if I plot those points here, -5 is going to -14, so that's about here. And then we've got -4 at -7. So -4, -7 is here. This point should be moved over a bit. And then -3 is at -6. -2 is at -5. And -1 is at a +2. So this graph now looks something like this. And you can see it's the same graph we had before. It's been just shifted to the left 3 units.
And in each of these examples, we actually didn't do the rule part. We just showed you what the graphs look like. But if we want to know what the rule would be, that means what would the equation come out to be. So if we look in this first example here, if we took f of x plus 2, well, I would take x cubed minus 6 and then add 2 to the outside, which means that g of x is actually equal to what cleaned up function? Well, that would be x cubed minus 4, because I would say -6 plus 2. And in example B, if we wanted to know what would that rule look like, well, if we were going to take find h of x by doing f of the quantity x plus 3, we would instead in this case, there we go, anytime we see an x, we would have plugged in the quantity x plus 3. So this would have become x plus 3 quantity cubed minus 6. Now, we've talked about different ways to multiply those out. So you can multiply that out on your own and check, but this would, if you multiply it out, combine like terms, and then remember to subtract the 6, this would become x to the third plus 9x squared plus 36x minus 21. So that would be plus 21. So, you could say that h of x is just equal to this first line with x plus 3 in parentheses cubed minus 6, or you could multiply it all out as well to get the rule or to get what the actual equation looks like. All right, so let's try another type of transformation which deals with reflection. And we're going to say in this case that f of x is equal to x cubed plus 5x squared minus 8x plus 1. So I'm going to write a function, g, that performs the transformation here. So this first one is going to be take f of x and reflect it across the x-axis. So we know if we reflect something across the x-axis, we're going from the top half of the graph to the bottom or vice versa, which means that in this case that changes our y value, which in a function means that we're going to change our entire function. So to start off, I would say that g of x, its rule is take your original function f of x and to reflect across the x-axis, we need to change our entire function. So to actually figure out what that rule is, we'll say we have a negative here, and then we need to distribute that into our entire f of x. So x cubed plus 5x squared minus 8x plus 1. So this would be our first step on how to find g of x. Again, to clean that up, we would say that g of x is equal to what value? Well, I'm going to distribute a negative into all 4 terms, and we will have a result of negative x cubed minus 5x squared plus 8x minus 1. Now, just to verify that we're correct, we're not going to graph this one by hand, but we are going to use our calculator to see what these look like. So we're going to start off by graphing our parent function, and then we'll go graph its new transformation. So parent function, x cubed plus 5x squared minus 8x plus 1. And again, hopefully you're graphing this as well. So that's our parent function. Again, we might want to change our window just because it is a little hard to see. So we're going to click on that top value and make it 25. You can even make it a little bit larger if you want to see where that top of that first part is. Okay, now let's graph its transformation. So we're going to graph g of x, so we'll add another function. It will be negative x to the third minus 5x squared plus 8x minus 1. And again, hopefully you're graphing this as well. We're hoping to see a reflection over the x-axis. Since we reflected, we now need to adjust how low this graph goes. So let's go down to negative 50, and you should be able to see that that's a very good visual in this case, that we do see it that reflects over the x-axis. The blue came from above, in some places to below, and below came to above.
Okay, we're going to try this with another example here. So again, we're reflecting polynomial functions. This one is f of x equaling x cubed minus 2x squared minus x plus 2. And we're going to write a function g that performs each transformation. Well, in this case, there's only one transformation. We're just reflecting across the y-axis this time instead of the x-axis. Well, if we want to reflect something across the y-axis, again, keep in mind, like if I had this little ordered pair, let's say 3, 1 right here, and if I want to reflect 3, 1 over the y-axis, I'm going to end up over here at negative 3, 1. So what changed? It was the x-coordinate that we made opposite. So whenever you want to reflect across the y-axis, you want to change the x's to opposite of x. All right, so in this case, we want our function g of x to be the same as f of opposite of x. So that's going to be opposite of x, quantity cubed, minus 2 times opposite of x squared, minus opposite of x plus 2. And so if we are going to simplify this a little bit, we know that negative x times negative x times negative x is going to be the opposite of x cubed. And I've got a minus 2 times negative x is a positive x squared. Minus a negative x is going to be a plus x, and then plus 2. So this is going to be our rule for g of x. And this function right here, when we graph it, should be the reflection of our original parent function over the y-axis. So let's test that. We are going to add a new page to our document here, and we're going to graph f of x equaling x cubed minus 2x squared minus x plus 2. So let's take a look at that graph. So that's our original parent function. And now let's see if we can get the reflection over the y-axis. So the new transform function is negative x cubed minus 2x squared plus x plus 2. And when we graph that, we see sure looks like it has been reflected over the y-axis. We have a mirror image right there with the y-axis.
Example 3 is going to talk about compressing and stretching functions, so horizontally and vertically. So in this case, our f of x function is 2x to the fourth minus 6x squared plus 1. And again, we'll graph these on our calculator to see the differences as soon as we figure out what it should look like. So first off, how will we describe this transformation? Well, we know that g of x is found by taking 1/2 out front multiplied by f of x. Again, anytime we have a constant multiplied out front, we're going to consider this a vertical change. And since it is a fraction, it is 1/2, which is less than 1, we'll call this a vertical compression of 1/2. So we want to see what would the rule for g be. Well, to find g, I will have 1/2 multiplied by f of x. So multiplied into 2x to the fourth minus 6x squared plus 1. So to figure out, the simplified version of g of x, I'll distribute a 1/2 to each term here. So in the first one, if I multiply 1/2 times 2x to the fourth, well, 1/2 times 2 will just give us 1x to the fourth. And then next up, we'll have a negative 1/2 times 6x squared, or wherever you want to put that negative. But 1/2 times 6 we know is a 3, so minus 3x squared. And then finally we'll have plus 1/2 multiplied by 1, which will just leave us with positive 1/2. So our g of x function, which is right here, if we were to graph that and we graph the original here, which is f of x, we should see that g of x is a vertical compression, which again, if I'm thinking about vertically, means up and down. We're kind of pushing it closer to the x-axis in that case. So let's graph these together on a new graph page on our calculator. So first off, again, hopefully you are graphing this with us to get used to typing in these higher powers. Our original is 2x to the fourth minus 6x squared plus 1. So there's our original parent function in this case, and we're hoping to see a vertical compression, so making it closer to the x-axis. So our transform function, x to the fourth minus 3x squared plus 1/2. Remember, hit Control divided by to get your 1/2 in a fraction setup. And as we graph this, it's exactly what we expected to see. Again, a vertical compression, if I look on a graph, means that this piece in green came closer to the x-axis here, here, and here. So I kind of grabbed it from the top and bottom and pushed my hands closer together.
Okay, let's take a look at this example. Again, we are compressing and stretching polynomial functions. This time we have f of x equaling 2x to the fourth minus 6x squared plus 1. And we're going to graph f and g on the same coordinate plane. Well, we're going to use our graphing calculator to do that. And we're going to describe g as a transformation of f. Well, if g of x is f of 1/2 x, we have that 1/2 is being multiplied by the x before we put it into the function. So you know that anytime you're multiplying the x by something, it's either a horizontal stretch or it's a horizontal compression. Well, in order to decide which, you need to take the reciprocal with these horizontal changes. If I take the reciprocal of 1/2, I get 2 over 1. Since 2 over 1 is greater than 1, that means it is going to be a horizontal stretch, not a compression in this case. So it's going to be a horizontal stretch of 2 over 1, or 2. So that's how we would describe g as a transformation of f. We'd say it's a horizontal stretch of 2. And so if we're going to actually write this function down, we are going to want to write that g of x is going to be, and I want to write f of 1/2 x, but that means I'm going to plug in 1/2 x wherever I see an x. So 1/2 x is going in here, and 1/2 x is going in here. So I have 2 times 1/2 x quantity to the fourth minus 6 times 1/2 x quantity squared plus 1. At this point, we need to do 1/2 x quantity to the fourth, but remember that's the same as 1/2 to the fourth times x to the fourth. Don't forget we still have this 2 out in front. And minus 6, and again here we're going to have 1/2 squared times x squared, and then plus 1. So 1/2 to the fourth is 1/2 times itself 4 times. That gives us 1/16, but that's still being multiplied by 2. And we have the x to the fourth, so that's going to end up being 1/8 x to the fourth. And here 1/2 quantity squared is 1/2 times 1/2, that's 1/4. That still has to get multiplied by the 6 and the x squared, and we do have that 1 after it. So we have minus the 6 over 4 can reduce to 3/2. So I have minus 3/2 x squared plus 1. So this is our g of x function. And so we are going to graph our original and this one on the same axis and hopefully see a horizontal stretch of 2. All right, so our original function, we're adding a new page to our document. Our original function was 2x to the fourth minus 6x squared plus 1. So that graph looks like this. And then we want to type in the transformation, which is 1/8. Again, if you do a control divided by, that pulls up that fraction template. 1/8 x to the fourth. And then we want another minus, and then another fraction template, 3/2, and then x squared, and then plus 1. All right, so it does look like this has been horizontally stretched. All of these points are being pulled further out from the y-axis.
So the example 4, we're going to look at how do I perform 2 transformations at once. Again, we'll have our calculator support our work and make sure we're doing the right thing here. So the first thing we're going to do is we're going to first take a vertical stretch by a factor of 3. So let's say we're going to call this one g of x. So to find g of x, based on our parent function f of x, we're going to vertically stretch. We're going to multiply out front by 3 times f of x. So let's perform that transformation first, and then we'll do our follow-up. So g of x is equal to 3 multiplied by x cubed minus 5x squared plus 3. Again, to distribute that in, and we'll get our cleaned up answer, it looks like g of x is going to equal 3x cubed minus 15x squared plus 9. Now, that wasn't the whole problem. The whole problem now said we also need to shift 2 units to the right. So we'll call h of x our whole transformation from that. But what we'll need to do here is we're going to need to go 2 units to the right. Well, we're not going to start back at f because we've already moved f and we've already changed it. So we'll actually say we're going to take our h of x will be found by taking whatever g was. So that's like our in-between step and going 2 to the right. Well, to go 2 to the right, we know we're going to have to adjust the x, so it's in the parentheses. So this will be x minus 2 to make it shift to the right. So wherever I saw an x in my g of x, I'm going to now replace that with the quantity x minus 2. And this will give us our final answer, kind of doing one step at a time. So h of x will equal 3 times x minus 2 cubed minus 15 multiplied by x minus 2 squared plus 9. Now, at this point, you really can just leave it like this in order to graph it. You could go through the whole process of cubing this and squaring this and combining like terms and multiplying, but there's really no need. If you can get your final answer here, and this does represent both the vertical stretch and the 2 to the right, performed in that order specified. You have to do this first and then this second, otherwise you will get a different answer. So please be sure you do that. But again, if you leave it like this, we're quite okay with you seeing your answer in this final form. So let's go to our calculator. We're going to add a new page. And we're going to say in this one that our original was x to the third minus 5x squared plus 3. Now, again, when we look at our final answer here, we are going to be hoping to see 2 different things happening. And we're going to adjust a little bit just so we can see a little bit better. I might erase these arrows we had from before. All right, so let's add in our final transformed function. So we're going to go to the tab key or control G, and we're going to add in 3 parentheses x minus 2, close the parentheses and raise that to the third power. And then we'll have minus 15 parentheses x minus 2, close those parentheses and square it, and then we'll say plus 9. So we're hoping to see a vertical stretch as well as a shift 3 to the right. So again, we'll adjust our window a little bit just so we can see where that's at. Maybe we went a little too high there. Maybe that's a little bit better. Okay, so again, what should you expect to see happening? Well, if it's a vertical stretch, we'll move our labels out of the way here. A vertical stretch is going to pull the graph away from the x-axis, which it looks like it did just that. Notice this part here in red is now up higher, and this part in red here is down lower. We can't see that part, but that's okay. Not only did it do that, but then it also took those values and moved them over to the right. So it both moved it to the right and it vertically stretched it by a factor of 3. Okay, so our last example.
Okay, so for this example, we're writing a function that transforms f of x equaling 6x cubed minus 3x squared in each of the following ways. Support your solution by using a graphing calculator. So we want to reflect this parent function. This is our parent function right here. We want to reflect that over the y-axis, which again means you're going to make all of the x's opposite. And we also want to shift 2 units down. And we're going to do this in that order. So to make our function, let's do the transformation where we're going to reflect over the y-axis first. So we're going to have 6 times opposite of x cubed minus 3 times opposite of x quantity squared. And I know that if I do opposite of x times itself 3 times, I will get a negative x cubed. So that's going to give me a negative 6x cubed here. And the negative x times negative x is a positive x squared, but multiplied by a negative 3 is going to give me a negative 3x squared. Now this all looks good, but then we still want to shift 2 units down, which means I really want to take this function and subtract 2 from it. So really, what are we doing? We're saying that g of x is equal to f of opposite of x minus 2. So I have the f of opposite of x right here, and I still need to do minus 2 at the outset of these. So this should be my new transformed function right here. So let's test that on our graphing calculators. We're going to type in 6x cubed. We're adding a new page. 6x cubed minus 3x squared There's our parent function, and then we want to have our transform function, which is going to be a negative 6x cubed minus 3x squared minus 2. So we see it's been reflected over the y-axis, and it's been shifted down 2 units. All right, that's it for this video.
Thanks for watching.